All right, this is the first lecture that we're going to do. This is pages 1 through 12 in the notes packet that I posted. So if I were you, I would print it off and follow along with me. Generally, I would be writing on an iPad and you'd be able to see what I'm writing. However, my pen and iPad are not currently working, so I have typed the notes on here today. So hopefully you can follow along with me and fill in your notes and answer any questions that I have for you on the video. So let's get started. Okay, so overview of chemistry in general. We are obviously going to learn a lot this semester, but what is chemistry? It is the study of matter and the changes they undergo. So when I'm talking about chemical reactions, that's how matter changes, why it changes, how we can make it change, those types of things. There's all kinds of applications and examples, of course, which I'm sure that you know. You might have been able to come up with the fact that chemistry is engaged in many other sciences, including geology, environmental science, which is a very large field to go into right now, physics. If you're looking into healthcare, chemistry is absolutely related in there. What does the molecule look like? What is it going to do? Biochemistry, of course, how the body works and the chemicals involved in that. Any type of food science or industrial science when you're trying to create things. And there's a whole bunch of other different applications as well. But this is kind of why we care about chemistry. It can be incorporated into many other different studies. So just one example of an application of chemistry that this was actually found in the 70s, answered the question, what happened to the dinosaurs? So, right, we say it was a meteorite, but how did we figure that out, right? There's actually this layer, and if you're looking at this mountain that I have in the picture, there's a KT boundary, so this really defined line, and this is actually off the coast of Mexico. It's in the Gulf of Mexico, right here. There's this big crater, okay? So this KT layer is actually the layer of sediment that was deposited between the Cretaceous and the Tertiary period, so right when the dinosaurs became extinct. There was unusually large quantities of iridium, and you might have heard of iridium before, you might not have. It's an element on the periodic table. Periodic table is what we use in chemistry. Iridium is actually very rare. It only comprises this very, very small percentage of Earth's crust. And when we find it, it is generally only because of meteorites that have struck the planet. So we can kind of put 2 and 2 together. There was this higher concentration of iridium, which must have meant that there was a crater right here. So they could figure out how big it was. They could figure out how big the impact was, how fast it was going based on the size of that crater. And that's how we were actually able to determine that this crater is most likely the cause of what made the dinosaurs extinct. So just one example of the many applications that chemistry and the periodic table can have. Okay, so we're going to start at the beginning. We're going to start classifying matter, right? Chemistry is the study of matter and how we change it. So what is matter? Matter is anything that has mass and takes up space or has volume. Okay, so anything that has mass and takes up space is considered matter. And when I say it has mass, that just means it has particles in it. Mass is the quantity of matter in an object. Okay, so matter is generally comprised of these 3 categories: gases, liquids, or solids. You won't find very commonly matter in different states, but there are different states. There's plasma, there's Bose-Einstein condensate, but we're not too worried about those. Most things are going to be either a gas, a liquid, or a solid. Okay, so you should be able to look at a picture and tell me if that is a picture of a gas, of a liquid, or of a solid. A solid is always going to have a definite shape and a definite volume, so like a block of something, as you can see from the picture. A liquid is going to be fluid. It is going to have a fixed volume, meaning it's always going to take up the same amount of space, but if you put it into a container, it's going to fill up the bottom part, right? So it's not a fixed shape. If it's 20 milliliters, it's 20 milliliters. It's just going to fill the bottom of whatever container it is in. Okay, and a gas has neither a fixed volume nor a fixed shape, meaning if I put it into a container, it's just going to fill that whole container. So if I put it into a 20 milliliter container, the gas has a volume of 20 milliliters. If I put it into a 50 milliliter container, it has a volume of 50 milliliters. So a gas does have a specific number of particles, but no fixed volume and no fixed shape. Okay, so changes between any of these three states of matter, gases, liquids, and solids, are called physical changes. Any physical change is something that doesn't affect the chemical composition. So for example, water, whether it is a gas, water vapor, liquid, water, or solid, ice, it still has the chemical formula H2O. Okay, so changing phases is a physical change. Okay, so we're going to move on to classifying matter. Yes, it can be classified as a gas, a liquid, or solid. Those are the states of matter, but we can also classify it as pure substances or mixtures. So all matter can be classified as either a pure substance or a mixture. Most matter is a mixture. Okay, they have different particles, different combinations of pure substances. So anything that is comprised of more than one element, more than one compound, and we'll talk about how we classify those later as well. So mixtures then can be broken down into two different categories. There are homogeneous mixtures and heterogeneous mixtures. So a homogeneous mixture is where the parts of a mixture are in the same state. So like all gas, all liquid, or all solid. There's no visible boundaries. It is uniform throughout the mixture. So if I'm looking at a homogeneous mixture, I can't see the different parts, okay? So an example would be air. You can't see the different parts of air, though there are molecules of nitrogen, oxygen, water vapor, carbon dioxide. There's a whole bunch of different things in the air. So it is a mixture, but you can't see the different parts. So it is a homogeneous mixture. It has a smooth consistency throughout. You can think of it that way, okay? Tap water is also a homogeneous mixture. If you get water out of your tap at home, it has H2O in it, of course, but there's also other minerals in there. There might be fluoride that's added to treat the water. There are all kinds of other things in tap water, not just H2O. Now, if it was distilled water or just H2O, then it would not be a homogeneous mixture. And we'll talk about what that is in a bit. Okay, so the opposite of a homogeneous mixture would be a heterogeneous mixture. So this is one that is not completely uniform. You can see the different parts. Okay, so for example, chocolate chip cookies, right? You can see the different parts in a chocolate chip cookie. Blue cheese, you can see the different things in blue cheese, or dirt. One that might not have come to mind is milk. Milk is actually a heterogeneous mixture, specifically because if you do look on a smaller level, you can see the different parts. There are different molecules in milk. It's kind of like a colloid, and in that the other parts are like suspended. If you let milk sit for a really long period of time, it will separate. You would get a heterogeneous mixture. So if something has distinct layers or different parts, it's going to be a heterogeneous mixture, or if it has different phases, right? Homogeneous has same phases, heterogeneous has different phases. So all mixtures, so this includes homogeneous or heterogeneous mixtures, can be separated by some type of physical process. Note I said physical process here, not chemical process. So I should be able to separate a homogeneous or a heterogeneous mixture by its parts, either by pulling them apart, or sometimes it's a little bit more complicated than that. Two other ways to separate a mixture would be distillation. So you've probably heard of distillation before, right? If you get distilled water, how did that happen? Well, it actually is a method of separation based on volatility. And volatility is how easily something is converted into a gas. So if something is easily converted into a gas, it will turn into a gas, and then we can recondense it and collect it. So this picture over here is actually a distillation apparatus. So if I start, this is where I'm starting with this bulb over here, this flask, with salt water. Okay, so salt water is a type of mixture. If you have salt dissolved in water, you cannot see the different parts. This would be considered a homogeneous mixture, or a solution. That is another word for a homogeneous mixture, a solution. So if I have a solution of salt water and I heat it up, okay, water is going to boil much faster than salt, right? Salt has an extremely high boiling point. I'm not going to be able to melt or boil salt with a Bunsen burner, but water, I can't. So what's going to happen is I'm going to heat it. Water is more volatile than salt, meaning it will turn into gas more easily than salt. So as it heats, water is going to turn into steam or water vapor. It's going to go up, and then it's actually trapped. It goes through what's called a condenser. So there's actually cold water going around this condenser, and as the steam goes through the condenser, it actually turns back into liquid, and we can collect it over here. So that's how a distillation apparatus works, okay? Heat it up, the thing that's more volatile will boil and turn into steam, then we can condense it back down and collect it, and then we would be left with the salt still over here because it won't ever get to a temperature high enough to actually heat it and collect it. So this is one way to separate a mixture, usually a liquid mixture. Another method of separation would be crystallization. So if I wanted to actually get the salt out of water, I could let it sit out and crystallize. As the water evaporates, the salt is going to stay there and crystallize. That's how I could separate them. But if you have different concentrations, so meaning a different amount of stuff dissolved in other stuff, and we'll have a whole unit on that, you could get some to crystallize or turn into a solid, so you could separate it out of a solution. So there's just two of the multiple methods of separation. You will do more methods of separation in lab this semester. Okay, so we talked about mixtures. Now we said mixtures are made of pure substances. So what are pure substances? A pure substance is something that has a fixed composition. All of the particles look identical. So like water we were talking about earlier, if it was just H2O and all of the particles looked like H2O, it would be a pure substance. So just like mixtures, pure substances can be broken down into two categories as well. All pure substances are either going to be elements or compounds. Okay, so an element is something that cannot be decomposed. It cannot be broken down any further, no matter what process you do to it, except for nuclear, but that we'll talk about later. So these are actually things that are listed on the periodic table. Now, no, you guys will not have to memorize the periodic table, but you will always have access to one. So something is listed on the periodic table, it's an element, it's a pure element. Carbon, helium, anything that of those 118 elements on the periodic table are considered elements. Okay, if it's just that, it is a pure element. Now, things can also be compounds. This is actually going to be the most abundant of pure substances are compounds. And that's when you have two or more elements that are chemically combined, which really means that they are bonded together. So we've been talking about water, H2O. I know you all know the formula of water. That is a compound because it's H2O, meaning two hydrogens and one oxygen bonded together, and every single particle looks like that if you have a sample of pure water. Okay, same thing is true of salt. Salt is sodium chloride, NaCl. All of the particles look the same. They're an Na and a Cl. And carbon dioxide. All the particles of a carbon dioxide sample look the same. It is one carbon and two oxygens bonded together. Okay, so if all of the particles, which are the smallest piece of substance, look exactly the same, it's going to be a pure substance. So it's either an element or a compound in that case. Okay. Now, the only way to break down a compound, and I already said you can't break down an element, you can break down a compound, is through some type of chemical change. So we said up here that mixtures can be separated by physical processes or physical changes, while compounds can be separated by chemical changes. Chemical reaction is the only way to separate a compound. So for example, if you have liquid water, I can undergo a process called electrolysis, or essentially running a current through it, and get it to separate into its two elements, hydrogen and oxygen. So that's what this is actually showing here. Once I get them to separate, I get H2, that's how hydrogen exists, and O2, that's how oxygen exists over here. That is one method of chemical separation. Okay, so if you're actually trying to separate the elements in a compound, that would be some type of chemical reaction. Okay, so this is just a recap. I like this flow chart. All matter can be broken down into two categories. It is either a pure substance or a mixture. And if it is a pure substance, it's either an element or a compound. If it's a mixture, it is either homogeneous or heterogeneous. So this could be a really handy review to look back at later. Okay, so I have example number 1 here, and I will have you try this before I give you the answer. It says, identify each substance as a compound, an element, a heterogeneous mixture, or a homogeneous or homogeneous mixture, also known as a solution. Okay, so give this a try in the examples, and then I will share the answers. Okay, so you should have gotten that filtered tea is homogeneous. Once you filter out your tea, you just have your tea. You cannot see the different parts. Freshly squeezed orange juice should be a heterogeneous mixture. You can see the different parts. There's going to be pulp floating in there. A compact disc, you can tell how old these examples are. Nobody really uses compact discs anymore, but a CD, I would consider a heterogeneous mixture because you can see different distinct lines in it. Aluminum oxide, which is a white powder that contains a 2:3 ratio of aluminum and oxygen atoms. What that means is the formula is 2 aluminums and 3 oxygens, Al2O3, always. So if a particle or something has a fixed ratio, i.e. always 2:3, or for water, it's always 2:1, it's going to be a compound. So that would be a compound, aluminum oxide. And selenium can be found by itself on the periodic table, so that must mean it's an element. Okay, moving on to properties of matter. And I didn't mention this earlier, but you might have noticed I've got hyperlinks in each of the top of these headings, and those go to the textbook in case you want to read it, okay? All right, so there's different properties of matter. There's going to be physical properties and chemical properties. We're going to start with physical properties because those are the most simplistic. These are any characteristics that can be observed without making a change to it. So if you have a substance, you should be able to observe or measure a physical property. So this could be the mass or the volume or the melting point, something that you're not changing the chemical to actually get this measurement. Now, physical properties can also be broken down. There are extensive properties and intensive properties. So an extensive property depends on the amount of substance you have, i.e. mass, volume. Okay, if you have a substance and you measure its mass, it's going to change when you have different amounts, right? If you have 2 grams versus if you have 5 grams, you have a different mass for different amounts, a different volume for different amounts. Intensive properties, however, are things that do not depend on the amount. So the melting point, whether you have 50 grams of ice or 1,000 grams of ice, the melting point for ice is always 0 degrees Celsius. Okay, so melting point does not change depending on the amount. Same thing with density. The density of a substance is always the same no matter how much of it you have. That's why density can actually be very useful. That's why density is actually very useful. Things have fixed densities, so you can actually identify substances based on their densities. So I have some examples of extensive versus intensive properties up here to kind of give you something to reference. Okay. All right, physical changes. We already talked about examples of physical changes are going to be a change which doesn't affect the actual chemical. It changes just the form of matter, not its identity. So an example of that we said before was changing the state of matter. So something that is melting is a physical change. Also, if you dissolve something, that would be considered a physical change. So salt, for example, NaCl solid and NaCl dissolved, that would just be a physical change. One, you can get it back. That's kind of a good way to think about it. And also, it still has the same properties, right? It tastes salty. It's still NaCl. I didn't change the formula by any means. So dissolving would be considered a physical property. Ripping a piece of paper, physical change. The paper is still made of the same stuff. Okay, so those are physical properties and physical changes. So we're going to switch gears to chemical properties and chemical changes. Okay, so a chemical property is a characteristic that could be tested with a chemical reaction or change. Remember, we said physical properties you can see or observe without chemically altering it. Chemical properties, you have to actually chemically alter it to see if it has a specific chemical property. For example, the only way to test if something is flammable is to actually light it on fire, and that would be a chemical change. So flammability, acidity or basicity, reactivity, any of those things are considered chemical properties. Now, a chemical change, on the other hand, is that reaction when you're actually changing the chemical formula. Whenever you break or make new bonds, it's considered a chemical change. So if something is rusting, that would be considered a chemical change. Burning wood would be considered a chemical change. Okay, so just make sure you're using those terms correctly. A chemical property versus a chemical change? Well, to find a chemical property, you might have to undergo a chemical change. Just make sure you're using the terminology properly. Okay, so example number 2, would these common daily activities classify as a physical or a chemical change? I want you to give this a try and then check your answers. Okay, so getting a haircut is just changing the shape of your hair. That should be considered physical. Applying bleach to turn your hair blonde is a chemical change. A lot of the time, a color change indicates a chemical change. Baking a cake is a chemical change. You're actually causing a chemical reaction to occur when you're heating it up. Adding crystal light packet to water would be a physical change. Remember, I said dissolving is a physical change. Leaves on a tree turning red or yellow is a chemical change. It's actually a different chemical that presents that color. Rubbing alcohol evaporating from your skin would be physical. Evaporation is just turning from liquid into gas. That would be a phase change, so it's physical. And pouring spaghetti sauce over pasta, I didn't make any chemical alterations. That would also be a physical change. Okay, on to units of measurement. So you might have heard the term SI units before. Those are the international system of units, the ones that we use all over the world. They are an agreed upon set of base units. You will use these. Okay, now I have all 7 of the base units listed here. However, really, we're going to use the first 5. Electric current and luminous intensity are really more physics related measurements, but we definitely will be doing length, mass, time, temperature, and amount of substance. Those are all relevant in chemistry. So you are going to need to know the units and their symbols. You've got the meter is M, kilogram is kg. We also measure things on a smaller scale, so you will see grams, that is just a G. Seconds is S, Kelvin is K, capital K, and a mole is MOL. I know it's only 1 letter shorter, but we still do use that as the symbol for a mole. Can't use M because M is already taken by meter. Okay. Now I also have some pseudo SI units, which are really derived units, and I'll talk about what a derived unit is here in a minute. But we often will use a liter as our base unit for volume, or liquid volume most of the time, and a metric ton, not a ton in English, is 10 to the 3rd kilograms. Okay, that's one you will need to know. And then the atomic mass unit, or AMU, we will use a lot as well. You can convert into kilograms, and we will be using atomic mass unit often as well. Okay, so now onto the metric system. You're probably familiar with the metric system already. Metric system is based on units of 10. They cause really easy conversions between different numbers, small and large. These are the abbreviations, the most common abbreviations. And what I've circled in purple, you should also circle. Those are the ones that we will use most of the time. Okay, so kilo is 10 to the 3rd of the base unit, which would be grams in our case. Centi is 10 to the -2nd grams, milli 10 to the -3rd, micro 10 to the -6th, and nano 10 to the -9th. Okay, so we use a lot of small scale things, so you will see these, and then kilo is our large scale that we usually use. Nothing bigger than kilo generally. You might see a mega every once in a while, but that's going to be it. Okay, and if you need help with metric conversions, you might want to check out my website. I do expect you to be able to use these numbers and reference them. I do not expect you to memorize all of these. Okay, this class is not based on memorization. It is based on application. All right, so okay, now for measurements we are going to be making in class, in lab, really. An important thing to point out is the difference between mass and weight. When I tell you to measure something in the lab, I'm going to tell you to mass it, not to weigh it, because we care actually about mass. Now, what's the difference? Mass is the amount of matter, usually in grams or kilograms, that something has. So how much stuff is in it? Now, notice on this example, my mass on the moon and my mass on the Earth are exactly the same, 120 kilograms, because the amount of stuff in my body has not changed. Okay, so the mass does not change based on gravity, whereas weight does. Weight is actually a measurement of the pull that the Earth has on you or the moon has on you. So notice the weight actually changes, and this one is measured in newtons, but pounds or newtons, that actually changes whether we're on the Earth or on the moon. Now, yes, I know we are not going to be on the moon. We are not going to be changing our force due to gravity, but mass is always going to be more applicable because it does not change, okay? So when you're in the lab, when I ask you to do things, what I want you to do is mass it. You're going to use a balance to take the mass. Okay, so let's move on. Temperature conversion. So we're going to measure masses. You definitely are going to have to measure temperatures in the lab. So there are 3 different temperature scales. They are based on different things: Kelvin, Celsius, and Fahrenheit. You do need to be able to convert between all 3 of these. So I have not necessarily the definition, but what they are based on. So you may not know, Kelvin, which was the base unit that I mentioned earlier, is actually based on the kinetic energy of molecules. Okay, if they have 0 kinetic energy, meaning they're not moving, that is considered absolute 0. Okay, so molecules at 0 would be not moving. Now we haven't gotten there, maybe someday we'll get close, but not moving is absolute 0, 0 Kelvin. The more movement there is, the higher the temperature. Okay, so Kelvin is based on kinetic energy of molecules. Celsius is based on water's melting and boiling point. So water melts or freezes at 0 degrees Celsius, and it boils at 100 degrees Celsius. So at 100 degrees Celsius, so it's actually based on water. So what is water doing? Fahrenheit, on the other hand, you may not know, is actually based on how we feel, how a person feels. Okay, so like if it's 100 degrees outside, that's like 100% hot. But that's really why we use Fahrenheit, because it's more relevant for us and how we feel as humans. So you do have to be able to convert between all of these. This picture is going to be really helpful. But these are the equations to convert. These are things that I would give you. Again, this class is based on application, not memorization. So Kelvin is degrees Celsius plus 273.15. And Celsius is equal to Fahrenheit minus 32 times 5/9. So you do need to practice applying these. These answers are going to be on any work that I give you, or sorry, these equations are going to be on any work that I give you, but you do have to be able to use them. Okay, example number 3, a student with a fever has a temperature of 103.5 degrees Fahrenheit. Express this temperature in degrees Celsius and Kelvin. Now watch your order of operations when you're converting from Fahrenheit to Celsius. If you need help with the algebra, please let me know. Now, hopefully what you did is you actually tried to convert these using your calculator or writing out the work. If you just looked it up online, that's not going to help you in the future. You are not going to have your computer with you when you're taking the test. So make sure you can actually do these calculations. You should have gotten that Celsius is 39.72 degrees Celsius and Kelvin is 312.9. Okay. All right, moving on. I mentioned derived units earlier. These are really any units that are composed of 2 or more SI units put together. So 2 different measurements combined. So density, for example, is a derived unit. It is mass divided by volume. You can measure the mass of something, you can measure the volume of something. The density is the ratio of those 2. Velocity is also a derived unit. It is distance over time. So really any units that are not those base units or those base SI units are going to be derived units, something created from multiple measurements. Okay. All right, and our last part for today is based on uncertainty in measurement. So if you took a class in high school, you might have talked about things called significant figures. We are definitely going to be talking about this today and how to make correct measurements. Chemistry is all about making measurements. Can you get the amount of stuff that you want to make in the lab? Can you measure the density? Can you identify what the substance is based on measurements? So measurements are extremely important in chemistry. So we have to make sure from the get-go you're measuring correctly. Okay. So first of all, there's 2 words that you need to know the difference between of what they mean. And those are precision and accuracy. Now, yes, we want to be both precise and accurate in our classes in our labs. Sometimes that's not always the case. You may not be able to affect the precision from which you are doing things, but we want to be both. Okay, so precision in one word means consistency. The more precise you are, the more consistent you are. So we want very precise tools. If I'm measuring a block on a scale over and over and over, I should get the same answer over and over and over. If I'm not, it is not a very precise scale. okay? Accuracy is how correct you are. So if you actually get close to the value you are supposed to, hopefully we can be accurate. Sometimes we can't actually guarantee that we are going to be accurate, but we want to compare with what we are supposed to get. If you are very accurate, you're going to have a very low percent error. So you got the correct answer, okay? All right, so if you look at, I like using these examples to determine the difference between precision and accuracy. If you look at these 3 dartboards, okay, this guy over here might be pretty good if we're not actually shooting for the bullseye. He's very precise. He's hitting the same spot every single time. That's usually what you're going to see from our instrumentation in the lab. It's pretty precise, which is great. But it's not accurate. No, so we're talking about if he was aiming at the bullseye. He's not hitting the correct spot. He's just very close. Now this guy is precise and accurate. He's hitting close to the same spot every time, and it's going where it is supposed to. Now this guy on the end is just terrible at darts. He is neither precise nor accurate. Okay, they are not close together. They are not near the bullseye. Now notice I don't have one on here that says accurate, not precise. You can't actually be accurate unless you are also precise, because if you don't have consistent data, you don't have enough data to actually say that you are accurate. So you cannot be accurate, but not precise. Okay, so I have an example here. It says, consider the results of 3 students who repeatedly weighed a lead block known to have a true mass of 10 grams. Okay, so on these graphs here, I've indicated by the solid horizontal line where 10 grams is. That's what they should have gotten. Okay, that is our theoretical value. A comment on their accuracy and precision. So take a minute to look at this data, see if you can see who was precise, who was accurate, who was both. Okay, so if I am looking at these, and the graphs I think tell a little bit better. This guy, that does not look like very precise data, right? It's kind of all over the place. I got really high, I got really low. He's got a high standard deviation, which would indicate he's not very precise. Now remember, I said you can't be accurate if you're not precise. So he's not accurate either. Yes, the average is 10.13. It's not that close to 10. So this guy would be considered neither. Okay, if you're looking at student B, these are all very close together. Okay, all of their measurements are around 9.8, which is great. He's very precise. Maybe his scale is off a little bit, but he's not accurate because he's not that close to 10.00, which is what he's supposed to get. Okay, so I want you to be very precise in the lab. Hopefully that also means we are going to be accurate, but precision is something you can actually control. Okay, student C is of course both. All of his measurements are really close together, and he got 10.01, which is very close, has a very low percent error compared to what he should have got, which was 10.00 grams. Okay, on to numbers. So exact numbers. These are numbers that we know 100% for certain. That would be anything you count, right? Counting numbers. If I can actually count the fingers on my hand, I have 5. That is an exact number. That is not any estimation whatsoever. Also considered exact numbers would be precise definitions. So like the definition of 1 foot is 12 inches. Okay, so that is an exact number. Okay, that is important because then we're going to start talking about numbers that are not exact. Most measurements are not exact. 12 eggs in a dozen, that's like a definition. A dozen is 12 eggs exactly. All right, so these are exact numbers, counting or precise definitions. Everything else, any measurement you make, is technically an inexact number. Okay, even if it's electronic things round their last number as well. So any measurement that you make is going to be an inexact number, have some level of uncertainty in it. Okay, so for example, a coin has a mass of 2.52 grams. If I put this on a scale, you might notice that that last number kind of wavers a little bit, and that is because the scale estimates that last digit. Another example would be a bottle of soda has a volume of 591 milliliters. Well, why don't I have it at 591.0 milliliters or 0.0000 milliliters? Well, I don't actually know those numbers. So how measurements are made is that you are always going to have multiple or hopefully multiple numbers that you know for certain, and then the last one is going to be estimated, and I'll talk about that more here in a little bit. So you should be able to tell the difference. If I'm looking at these examples here, tell me if they are exact or inexact or measurements. Okay, so we need to look at phrasing on these. So for example, a store has 35 bicycles on display. That would be exact. I can count 35 bicycles, right? The density of an object is found to be 1.8 grams per milliliter. I would consider this measured because found to be would mean that I measured it in the lab. Okay, so things in the lab are going to be measured some degree of uncertainty. 1 meter is equivalent to 100 centimeters. Well, that's definition. The definition of 100 centimeters is 1 meter. They are the same thing. That is exact. Planck's constant is listed in the book as 6.626 times 10 to the negative 34th joule seconds. That would be exact. Any type of definition is an exact number. There are about 454 grams in 1 pound. Well, that would be measured. It sounds like they are estimating, right, about 454 grams in 1 pound. If you actually looked it up, however, that would tell you the exact number. So there's a difference between exact and measured. Okay. Now we're going to go more into measured numbers. Okay. Any measured number, like I was mentioning before, has some degree of uncertainty to it. We are not 100% sure of all the digits in a measured number. So we need to count what are called significant figures. So if you break that word down, significant means important, right? So which numbers, which figures are important? Those are the digits measured that are certain or have a graduation line on the instrument plus 1 estimated digit. So this right here is a measurement. Say I measured a piece of wood and it was 5.213 centimeters. Well, I know for certain the 5, the 2, and the 1, and the last number is estimated always. Okay, so certain digits are ones that everyone would agree on. So if I'm looking at a ruler, everyone can agree that this was somewhere between 5.21 and 5.22. Okay, those are known numbers. The 5.21 I know for sure. Okay, the uncertain digit is the best guess. It is the last digit in your measurement. Okay, so the last digit in this one, well, this person looking at that piece of wood thought that it was at 5.213, but it might have been at 5.212 or 5.214. We're not sure. Okay, so the last digit, again, in any measurement is going to be your uncertain digit. All right, so here I've got a measurement. It's marked here at 2.55 or 2.5 on these two different rulers, but notice the two rulers are different. Okay, the more graduations you have, the more lines, the more precise your measurement can be, the more significant figures or digits you can have. Okay, so when I'm talking about certain digits, if you actually look at this first ruler here, my line, I know that that's somewhere between 2.5 and 2.6. So that 2.5 part is known. It is for sure between those two marked lines. Okay, now I think it's right in between those two lines. If you were looking at it, you might think it's a little bit closer to the left line. You might put 2.54. You might put 2.56 if you think it's a little closer to the right line, but I think it's right in between. So it's 2.55 to me. So that last digit is estimated. Okay, now if you're looking at the second ruler, it doesn't have as many graduations. We can all agree that this line is somewhere between 2 and 3, right? So it's 2 point something. Okay, so that is a certain digit, but I'm actually estimating that that's at about a 0.5. You might think it's at a 0.6 or a 0.4. So that last digit is estimated. So essentially any measurement you make should have what you have graduations for. So however many lines you have graduations for. So for example, this ruler has graduations for the 10th place. That's this 5 right here. And then you estimate 1 more. So I estimated to the 100th place on this one. If you're looking at this ruler, I have graduations or markings for the 1's place. That's the 2 right here. And I estimate 1 more digit, or I estimated the 10th place in this example. Okay, so read what you have lines for and then estimate 1 more digit. All right, so we're going to do some examples here. Oh, I already put the answers on here, but give these a try. These are my examples, okay? So this is a piece of red whatever that's measured with this ruler and this ruler, okay? I can get a different measurement on these two rulers because one is more precise or has more graduations than the other. So the first one is somewhere between 4 and 5. I said it was 4.5 centimeters. It might be 4.4, might be 4.6, depending on what you thought those would be acceptable answers. Okay, that 5 was estimated. However, if I use this ruler, I can definitely see that it's somewhere between 4.5 and 4.6. So I said it's 4.55 centimeters. You might have said 4.54 centimeters or 4.56 centimeters. Those would all be acceptable answers because that last digit is estimated. Now, if you think something is right on that line, okay, so I know, well, it looks like it's right on the 3 to me. You can put a 0.0, okay? So essentially, when you look at this ruler, I have markings for the ones place, right, where that 3 is, which means I need to estimate the next digit. So I did, I thought it was a 0, so I put 3.0. Okay, so 0 is an acceptable number to put as your estimation. Okay, you should just always have one more digit than what you have markings for. Now, if we look at this graduated cylinder, and you guys are going to be looking at a lot of graduated cylinders this semester, water always does this little dip thing. It's called a meniscus, okay? So you always need to measure from the bottom of the meniscus. So how much is this based on the bottom of the meniscus, okay? So this to me, now I'm gonna look at my graduations, make sure I read this correctly, right? So this is a 6 and this is 8. So if I count the graduations in here, well, this one here is actually 7. So what each of these graduations counts for is a 0.2. Okay, so if I count up here 6.2, 6.4, it's somewhere between 6.6 and 6.7. Sorry, 6.6 and 6.8. So I said it was 6.7. I think it's right in between. You might have said it with 6.6. You might think it's right on that, and that's okay. That would be fine. That last digit is estimated. All right, so that's what I would put this one at. Remember to read from the bottom of the meniscus. Okay, so we're gonna look at this equipment. This example says, which measuring apparatus would you use to deliver 9.7 milliliters of water as accurately as possible? And then to how many significant figures can you measure that volume of water with the apparatus you selected? Okay, essentially, the more graduations, the more precise your measurement. Okay, so if you're looking at all of these, I would say that this first guy has the most graduations because it has a line for every ones place. This one is for every tens. This one is also for every tens. And this one you can't see very well. This is a really teeny tiny beaker. Beakers are never very precise. You should always stick to graduated cylinders. So I would pick this first one as the best measurement tool, okay, to get 9.7 milliliters of water. Now, if I needed over 10, I would have to use bigger graduated cylinder, but this one is correct. So notice it has lines for the ones place, so I can measure one past that, or I can estimate one past that. So 9.7 would be a measurement you can make from this graduated cylinder. All right. So how do you know how many significant digits something has? Okay, the important numbers. Okay, so sometimes I will just give you measurements. Okay, if you look over here, we have a bunch of measurements. And then I told you how many significant digits or significant figures are in each measurement. So 312 has 3 significant digits in it. 0.020 has 2 significant digits in it. So what does that mean? How do you know if something is a significant digit or not, depending on how you wrote it? Okay, so there are some rules, and you can probably figure them out from looking at these measurements, what the rules are. First of all non-zero digits are always significant figures. I just wrote SF. Okay, so all numbers that are not zero, so 3, 1, 2, that has 3 significant digits, all of those numbers are significant. Okay, now that's the only one that's all non-zero. So I'm going to get to the zero rules because those are the most difficult. Zeros before the first non-zero are not significant figures. So what I mean is zeros at the beginning of a number before the first actual number or non-zero are not significant. So if you look at 0.020 here, these first 2 zeros they're not significant. Those are considered placeholder zeros. The 2 here and this 0 are significant. So zeros beforehand, so this one here, zeros before that 7 don't count. Okay, the 0 before this 8 doesn't count. Zeros before this 2 don't count. All right, so zeros before the first non-zero are not significant. Sandwiched zeros are significant. So what that means is if there's a 0 between 2 numbers or 2 non-zeros. So this example here, got a 9040. Okay, the 0 between the 9 and the 4 is significant. 0 on the end in this case is not. This only has 3 significant figures. 0 right here is 0 between the 2 and the 5 in this number are significant. Okay, so zeros in between are significant. And then if you're looking at the ones at the end, there is a rule that tells you when they are and when they're not. Okay, so let's review really quick.
Zeros before the first non-zero don't count. Sandwich zeros do. And zeros at the end, it depends. What does it depend on? If there is a decimal somewhere, if there's a decimal somewhere in the number, then the zeros at the end or to the right do count. Okay, so I want you to use these rules to figure out how many significant digits are in each of these numbers in example 7. Okay, try those and then check your answers and let me know if you have questions. Okay, so A only has 2 significant digits. Remember, zeros before the first non-zero do not count. B has 3 significant digits. That 0 on the end does count because there is a decimal place somewhere in the number. Okay, it's right here. There's a decimal. Okay, if there's a decimal anywhere in the number. 9.20 has 3 significant figures. There is a decimal, right here. So the zeros at the end do count. This one only has 2. Okay, the zeros at the end don't count in this case because there is no written decimal. And this one, oh, that's wrong. This one has 5 because there is a decimal. The zeros to the right count. Well, and that would make these ones here considered sandwich zeros, or there are also zeros at the end. Those do count because there is a decimal. So all those zeros at the end are going to count if there is a decimal. All right, if you need more practice with this, there will be some in the homework. All right, so this should hopefully be a review. Scientific notation. We're going to use really, really big numbers in this class and some really, really small numbers. If you think about it, we're talking about molecules, atoms. If I want to know how many atoms are in something, it's going to be a very large number. So we have to be able to express those correctly. So just a really quick review of scientific notation. Writing things in scientific notation should look like this. Some number in decimal form times 10 to some exponent. Okay, a couple of notes. That number in the front should always be between 1 and 10. So if you're trying to figure out how many times you got to move your decimal place, always move it so that you have one number in the front of your decimal place when you're writing in scientific notation. So if you look at examples A, B, and C here, example A, I've got 9.3 in the front. I moved the decimal place all the way to go to 9.3 because that is between 1 and 10. B is 5.114 because that decimal place gets me a number that's between 1 and 10. And C, I moved that decimal 3.34. Again, it's a number between 1 and 10, or in this case, -1 and -10. Okay, but your front number needs to be between 1 and 10. Now then, how do you figure out that exponent in the scientific notation? Well, instead of trying to remember if it goes left or right or what that means, because some people end up switching them in their mind, if you have a negative exponent, that means it was a very, very small number. And if it's a positive exponent, that means it was a very, very large number. Okay, so if I was converting A here into a scientific notation, I would move the decimal. Okay, now there's no written decimal, so you assume it's at the end. How many times to make my front number 9.3? So I would go 1, 2, 3, 4, 5, 6, 7. So I move the decimal place 7 times. So that means it is 9.3 times 10 to the 7th power. Now I have a positive exponent because this is a very large number. Okay, B, I moved the decimal 5 times to get it to 5.114 times 10 to the, now I wrote -5th because this is a very small number, so it needs a negative exponent. Okay, so keep that in mind, give these a try to get these into scientific notation just to make sure that everybody's on the same page. Okay, I have each of these written out, so make sure that you did them correctly. You might even have a scientific notation button on your calculator, and that's fine. Go ahead and use that. One thing I wanted to point out here is how to count significant figures when you're in scientific notation. Actually, it's super easy when you have numbers in scientific notation. It's anything to the left of the multiplication sign is significant. So this first one has 4 significant figures. B has 3 significant figures, and C has 5 significant figures. So anything on the left side of a scientific notation number is considered significant. Another thing to point out is when you're putting a number into scientific notation, you should keep the same number of significant figures. So this last one is a really good example. If I look at this number and I said, how many significant figures does this number have? You would be like, well, 2, 1, 0, that's 0 sandwich, 6, 7, those are all significant. There's no decimal place written. So this has 5 significant digits. The zeros at the end do not count. Okay, so my number in scientific notation should also have 5 significant digits. That's why I put just 5 numbers here, times 10 to the 10th. Okay, if you need help with scientific notation, please come see me in office hours. Okay, we're almost there. Last thing I need to talk about is using significant digits in calculations. So your first lab is going to be based on density. Density is mass over volume. You're going to have to do calculations with these measurements. You're probably almost always going to have to do calculations with your measurements. So it's important that you know how to use significant digits when you're doing math with them. Okay, so one thing to remember and how we determine the rules for this is you can only be as precise as your least precise measurement. So what that means is you're only as good as your worst measurement. You can't claim that you know to 7 significant digits what the answer to a problem is if your scale only gives you 1 decimal place. So it says you have like 2.2 grams. I can't claim to know all of these digits exactly if my scale isn't very good. Okay, so if you are rounding incorrectly and giving me a bunch of significant digits, you're actually lying to me about how good your data is. Okay, so you do need to be careful with this. You need to round correctly. So what are the rules for rounding when we do math with measurements? Okay, pretty easy. Multiplication and division. You need to round your final answer to the least number of sig figs. You'll hear me abbreviate significant figures as sig figs. Okay, so what I want you to do is I want you to look at the numbers in the problem that I give you. Whichever one has the least number of significant figures, that's the same amount of significant figures that your answer should have. Okay, same thing in the lab. If you're making measurements, your final answer, if I asked you to find the density of something, it should have the same number of significant figures as your measurement that had the least significant figures, the one that was the worst. Okay, now addition and subtraction is a little bit different because of how that works. You should round your final answer to the least number of decimal places, okay, meaning numbers after the decimal. So again, you look at the numbers in the problem or the measurements that you made in lab, you do your math, and then if it's addition and subtraction, you round to whatever your least number of decimal places was. Okay, now rounding works the way you have always learned how to round. If the next digit is 5 or bigger, you round up. If the next digit is 4 or lower, you keep the number the same. So if I said round this number to 2 significant figures, okay, if I said round 5.37 to 2 significant figures, you want to look at the second significant figure. That's where you're supposed to round. It's 3. Okay, and the number after it is a 7, well, that should round to 5.4 then. So the number 5.37, if I want to round it to 2 sig figs, is 5.4. Okay, 5.34, okay, rounds to 5.3, right? The number after the 3 is 4 or lower, so I'm going to keep it the same number. It rounds to 5.3. 5.35, okay, the number after my second significant digit is a 5. I would round it up, so this rounds to 5.4. And if I gave you this number, 5.349, and I said round it, again, I want you to look at the number just directly next to the one you're trying to round. After the 3 comes a 4, so it does not round up, it's just 5.3. Okay, so regular rounding rules. Now, don't think too much into this. If I say round to 2 significant figures, well, just find the second significant figure. What that really means in this first case, 5.37, is that I want you to round to the nearest 10th. It's like saying, please round this number to the nearest 10th. Okay, it's like saying, I gave you 5.349, please round this number to the nearest 10th. Okay, so find the second sig fig and round there. All right, now what if you had a series of calculations? So I had to multiply this and then divide this and then multiply this and divide this. Don't round to the very end. Okay, this is another reason that you should have a scientific calculator. Keep all of your numbers. Don't round to the end. Okay. Okay, and the other rule is if you have mixed calculations, like you have sum, addition, and subtraction and multiplication and division, you have to kind of use your rules for each operation. Okay, so be careful when you're doing these. Okay, so I have some examples here. I want you to try to round these. Now, I already did the math for you. I know you can use your calculator, fine. But I did this and I want you to round it correctly. So try these and then check your answers. Okay, I have all of the answers for these written right here. So check your answers. There's a couple that I want to point out, and those are part C here. When you multiply these, your calculator gives you 0.059964. Again, I don't want all your calculator numbers. I want you to round to the correct number of significant figures. Well, this answer should have 2 significant figures because this number here, 0.0057, only has 2 significant digits. Okay, so I would be like, okay, I want to round to 2 sig figs. Well, where's my second sig fig? Well, it's the 9 here. It's got a 9 after it, so it would round up. So this would actually be 0.060. Now this does have 2 significant figures in it, right? The 6 and the 0 both count, okay? This one, 69.72 minus 67.92 gives me 1.8. That's what my calculator says. However, it's not the right number of significant digits. When I do subtraction, I need to round to that says the least number of decimal places. Well, both of these numbers have 2 decimal places. So my answer should have 2 decimal places. So you might have to add a 0. Okay. Now rounding big numbers can be a little tricky. Don't overthink it. Okay. This number and this number here in part E, 0.23 only has 2 significant digits. So my answer should have 2 significant digits. Okay. So I got this number in my calculator. This 2152.17 blah, 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 blah. And I only want to round to 2 significant digits. Well, that means I want to round to this number 1 right here. Now it's got a 5 after it, so it's going to round up to a 2. However, this number does not just round to 22. Okay, 2,152 does not round to 22. It does round to 2,200. So you can put those zeros there as placeholder zeros. Now this answer has 2 significant digits, and that is how you would round it. Okay, now these mixed ones are a little bit more difficult. So what I did here is what you need to do is the subtraction first, right? Order of operations in my parentheses first. So once I do the subtraction, my answer there should have had 3 decimal places due to subtraction. Okay, so 3 decimal places. And if I did this math, that number actually only had 3 significant digits. So then I do my multiplication and I go by significant digits, and it should have 3 significant figures. So that's why I reported 2.50. Okay, this one here, again, I did my addition first. That should have only had 1 decimal place because both of those numbers only have 1 decimal place. And this number, when I added these together, actually had 4 significant figures when I did the math, and I rounded to 1 decimal place. And so that had 4, and 180.5 also has 4 sig figs. So my answer should have 4 sig figs. Okay, and finally, I subtracted these 2 first. It should have only had 1 decimal place because 4.5 only has 1 decimal place. So that number had 3 significant digits, and I divided it by a number that had 4. So my final answer should only have 3 significant digits. Okay, so you do need to watch in your series of calculations that you do find your correct significant digit, but again, don't round until the end. So keep those numbers in your calculator. You just do have to know where to round. So be careful with those. And if you need more practice, let me know I have it. Oh, that's where we're ending for today. If you have questions, please come to office hours or send me an email. I will be happy to help you.